All right, so this is our second chapter on internal flow. And last time, it's almost like I wasn't even teaching heat transfer, was I? I was reviewing fluid mechanics. It was everything to do with the hydrodynamic considerations. But we have to get the fluid flow right, and then we add on top of that the thermal considerations. So today we'll get to the thermal considerations, but there's one other little topic on the hydrodynamic that I want to cover. So let's jump into it. A very interesting result that for laminar flow that's fully developed in a pipe, that you have the friction factor as a constant 64 over the Reynolds number. We see that on the Moody diagram where you have the Reynolds number. And then in this region where it's less than around 2300, that's laminar flow, they have a straight line on the log-log plot for the friction factor as a function of the Reynolds number. So that equation is F equal to 64 over the Reynolds number. Well, let's go ahead and reestablish that. So we go back to the definition of what the Reynolds number is. The Reynolds number is rho u mean d over mu. And then last time, for laminar flow that's fully developed, we were able to derive the quadratic expression for the velocity profile. And in that, we were able to get the relationship that the mean speed in the pipe, or mean velocity in the pipe, is equal to d squared divided by 32 mu minus dp dx. I tried to do that last time, but I ran out of time. That's one of the main results, that we have that constant, and so the profile, if you recall, u as a function of r is equal to 2 times u mean times 1 minus r over cap r quantity squared, and that's what we were able to derive, this u mean constant. And then 2 times the mean velocity is the maximum velocity. The definition of the friction factor, is minus dp dx times d divided by 1/2 rho u mean squared. At this point, I'd like to multiply it just by 1 so I don't change anything. But I need a special one for things to convert. So we take a look at this equation right here, and I can rewrite this equation to make it look like 1. U sub m 32 mu divided by d squared minus dp dx. Is that 1? Is this equal to 1? Sorry, I tucked it in there, but let's now multiply that. So we multiply by u sub m 32 mu d squared minus dp dx. And we're able to cancel the dp dx's. One of the diameters, one of the mean speeds or velocities, and we're left with this 1/2 flips up, and so we're left with F is equal to 64, 32 times 2. Then we have mu over rho u sub md. This term, I know it's upside down, but it's hard to see, but that's just the Reynolds number upside down. 64 over the Reynolds number. QED. So there you go. It's one of those important results. Now let's talk about thermal considerations. So we have flow in a circular tube, a long circular tube. So I'll sketch a circular tube. And we typically in textbooks I put a little bell mouth to it because you don't want to really get a recirculation region and a sharp-edged entrance to it. And we'll talk about the coordinate system x running down the length of the tube. And then also we talk about r going from the center line 0 to cap r at the wall. So lowercase r goes from 0 to cap r. All right. The flow comes in, and when it comes in, it's basically the beginning is a uniform velocity profile. And then as it feels the effects of the wall with the no-slip boundary condition, and the thermal boundary condition that the temperature is equal of the fluid is immediately adjacent to the wall is the wall temperature. Then we develop a temperature profile. So if this is our temperature profile, it comes in uniform. And then a little down the wall, you can sketch it where the surface is warm, and then like that. So this is sketched where the fluid's being heated by a warm wall. And so you get this propagation of a boundary layer until the thermal boundary layer as well as the velocity boundary layer, until it's fully developed at a distance right here. It'll be fully developed thermally. What does that mean about being fully developed thermally? If I take a look at the velocity profile right here, we'll still leave a warm wall. It'll come in something like this. So the shape no longer changes. It may boost up. Maybe the fluid as a whole is getting warmer, but the shape is pretty well established. All right. Well, what is the distance to become fully developed thermally? Well, it depends on if the flow is going to be laminar flow or turbulent flow. If it's laminar flow, it's the distance to be fully developed hydrodynamically, and we just multiply by the Prandtl number. What was that distance to be fully developed hydrodynamically? That was equal to 1/20th the diameter times the Reynolds number. And we took a look. We plugged in that equation, put a Reynolds number of 200, put a Reynolds number of 2,000, and you'll see that usually it varies between 10 and a little less than 100 diameters. It's pretty hard to have that long. And now you multiply by the Prandtl number, and that's the change for the fully developed thermodynamically.
Looking up again at the thermal entry line,
yeah.
Will at any point, with like an infinite length of tube, will the profile just disappear and become?
No, because what I'm thinking is we're always pumping the temperature heat into it. But yes, after a while, let's say that it's a constant wall temperature, and the bulk temperature everywhere inside could go to a flat, uniform temperature profile, yes. But as I sketch it, I'm always pumping heat into it. But if you make it real long and the constant surface temperature, yes. Yep. Okay. What about turbulent? Well, to be fully developed thermally is the same as the fully developed hydrodynamically, because the mixing associated with turbulence makes it fully developed quite quickly in the same mechanism, 10 diameters. Now we'll talk about the mean temperature. Review, what did we have before it? Didn't we have the mean velocity? What was the mean velocity? U sub m is equal to 1 over a sub c, the integral of u dA. So we had this velocity, that profile that varies as a function of r. So what we want to do is the same type of thing that we did to get that mean velocity equation. We want to do it for the mean temperature. So we're interested in a very simple expression for the rate of energy flow down the pipe. We'd just like to use the mass flow rate, the specific heat, and some representative temperature, the mean temperature. But we know that the fluid is flowing faster in the middle, and it may be lower temperature or higher temperature in the middle. So both the velocity is a function of location as well as the temperature of the fluid is a function of location. So to do it very accurately, we would have to integrate over the area. We'd have to consider not just the property rho c sub p, but u as a function of r and t as a function of r. So that's our starting point. Well, we expand what is the mass flow rate. It's rho times u sub m. I'm going to put the t sub m a c there and put the c sub p there. So I expanded what m dot is. It's rho u a. All right. And now we have the rho c sub p u t d a. We can cancel, and we find an equation for the mean temperature. It's 1 over the mean velocity times the cross-sectional area, integration over the cross-sectional area of u, which is a function of space and r. T is a function of r, dA. If you wanted, this is the big equation right here. We'd like to stop there, but if you wanted to say, what does it look like? It would be 1 over u mean pi cap r squared, integral from 0 to cap r, u is a function of r, t is a function of r, 2 pi r dr, t sub m. But this is the best place to stop. It's the equation for the mean temperature. There's a number of different names for this mean temperature. Sometimes they'll talk about the bulk temperature, or sometimes they'll talk about the mixing cup temperature. Well, so you take a pipe and it's flowing down, and just like we said, it's fast in the middle and slow on the edge, and maybe it's also hot on the edge, and maybe it's cooler in the middle. So it can be not only the velocity profile, but the temperature profile in that pipe. And if you conceptually take that whole content of the pipe and divert it, just maybe for a second or two, into a container that's well insulated, let that fluid mix, and you're just grabbing the whole package of fluid for an instant of time, let that fluid mix, you'll get a temperature that's uniform throughout that mixed cup. And if you measured that temperature with the thermometer, that temperature would be the mixing cup temperature, which is the same as the bulk temperature, which is same as the mean temperature. I'm not accounting for, expansion of the fluid as it comes out of the pipe at different pressure. Throw that out. I'm not counting for temperature-dependent density and temperature-dependent specific heats. Throw that out. It's just simple, constant density and the constant specific heat. So hopefully that mean temperature, that T subscript M, makes sense to you. So we want to talk about developing and fully developed temperature profile in a pipe. So let's talk about a pipe right here. And that pipe has a constant heat, surface heat flux applied to it. So everywhere along that pipe, I'm trying to sketch this Q double prime along the surface is equal to a constant. It's some constant heat flux applied to the wall of that pipe. And it's not going to be negative. It'll always be positive in our discussion right now. And what I'd like to do is I'd like to talk about different things that happen down the length of that pipe. I'd like to talk about the mean temperature. How does it vary as a function of position down that pipe? Maybe you think about this part right here at x equal to 0. That's the inlet region to the pipe, right? And maybe way down here it's close to getting out of the pipe. And right in this region, between 0, it's going to become fully developed thermally. So we do have a little bit of entrance region to the pipe. But for this problem, what is the best description of the mean temperature profile? Would it be just a straight line? Something that goes up a little bit and then goes to a straight line? Or something that starts off pretty flat and then goes to a straight line? And I want to draw all three of those with the same slope. So is it line A, B, or C? We're done? All right. Let me ask another question. Or should I just grade it? Just grade it? All right, just grade it. All right. So most people think that you have increase in the temperature that's more rapid on the inlet section of the pipe. And then it gradually is flat. But that's not the best way to describe this. There's a rate equation. Q double prime is equal to H times some temperature difference. Ts minus Tm is what's driving the flow into the pipe, isn't it? Isn't it the difference between the surface temperature and the mean temperature and the convection coefficient? For this problem, Q double prime, isn't it a constant for this problem? Okay. We also have one other equation that we'll use, and it's our energy balance. What is our energy balance for this problem? Something like Q double prime times the perimeter times some length from the beginning of the pipe to some position x. See what the perimeter times x, what does that give us? The perimeter is pi d times x. Isn't that some surface area? So Q double prime times some surface area is how much, the rate at which it's being added, but that has an effect of making the mean temperature go up in the flow, doesn't it? From what it does coming into the flow, into the pipe. How does it go up? By m dot C sub P. Does that energy balance equation make sense? What about this Q double prime here? Is that a constant for this problem? So I'm plotting the mean temperature as a function of location as I go down the pipe. It starts at the incoming value. And can you see what the solution is for the mean temperature as a function of location down the pipe? It would be the incoming value plus Q double prime Px divided by m dot C sub P. If I plot that as a function of x, what does it look like? Straight line, isn't it? Straight line. So B is the best answer. So now if we go back and look at this, something is happening in the entrance region. We're going to get to it. But before I do that one, let's talk about the temperature of the surface. Let's go out to this location. It's past being the entrance region. It's a fully developed region. And I want you to compare the temperature of the surface of the wall right there, temperature of the surface of the wall of the pipe, to the mean temperature of the fluid flowing in the pipe. And I want you to say, oh, I think the temperature of the surface is greater. Or the temperature of the surface is equal to the bulk or the mean temperature. Or the temperature of the surface is lower. Which one is it, A, B, or C? Is everybody in? Everybody's in? You're still thinking? All right, let's go ahead and stop. Sorry about that. But well, is heat being added to the fluid that's flowing down the pipe for this problem? Yes, it is. So in order to push the heat in from the wall, does the surface of the pipe need to be greater than the mean temperature of the fluid at that section? Yes. And so the best answer is, isn't it A? Isn't it A? All right. So that's the temperature there. You know, we could talk about a temperature difference, and we could call that temperature difference theta. Couldn't we? That would be, the theta would be equal to the temperature of the surface at that location minus the mean fluid temperature. Okay. It's fully developed. It's now fully developed. Will this theta be constant in that region? Will it be constant? It will be constant, right? Because the Q double prime is constant. So the H is constant, it's fully developed, etc. So let me ask this question. At this point, I want to now focus on, because you toggle between the mean temperature, surface temperature, fluxes, convection coefficient, H. Now the H, just in the fully developed region, H, is it a flat line? Does it still increase? Or is it going to decrease some as it goes further down the pipe? So is it A, B, or C? What does H, the convection coefficient, do? Which profile is best to describe H? Does it somehow does it increase with increasing distance down the pipe? Or is it constant down the pipe? That's a flat line. Or is it somehow decrease as it goes down the pipe? H, the convection coefficient. All right. So What does it mean if you're fully developed? The H is a constant. The convection coefficient is a constant. And so it was an easy question, I hope. I intended to ask some easy questions as well as some hard ones. So what about H in the entrance region? Does it maybe look like this? Or does it look like this? Or does it look like this? Is it more like A, B, or C? You should. All right, so I'll go ahead and stop. Well, what do we know about flow over a flat plate? Maybe that information would help us. What happened when the boundary layer was very thin at the beginning of that flat plate? What was the H? Was it high or low? High. It was high. We had a high H, thin boundary layer. Don't we have a thin boundary layer in the entrance of the pipe? And so it's going to be a high H. And so the best answer is... Good. Good. So now we know that in the entrance region, this is up to being fully developed hydrodynamically or thermally, both thermal and hydrodynamic. I'm going to put the Prandtl number to 1 and it'll develop at the same rate. So this is the entrance region. Now what I'd like to do is I'd like to talk about what does that surface temperature of the wall do. We already talked about the bulk or the mean temperature of the fluid, right? So does this come in and go pretty close to, or does it stay flat, or does it go like this? So answer A, B, or C. I'm sorry that I think you see what I'm trying to show. What does the temperature of the surface for this problem with a constant heat flux boundary condition applied to a flowing fluid through it? And we have now considered the entrance region. Does the profile look more like A or B or C? And in other words, what's happening to this theta, near the entrance? Is it small or large or the same as when it's fully developed? Let's go ahead and stop. And we'll see what we get. The H is higher, the delta T is lower for the same Q double prime. So what did you use? You used this equation. You said the H was higher, the same Q double prime, hence the delta T can be lower. And so that's the right answer, isn't it? All right. I think I'm about ready to leave this alone. You want one more question? All right. I'll give you one more question. Somebody says that the profile we understand is like this. Let me try and sketch it more accurately. Okay. Somebody says, no, the temperature profile is this for the surface. And it does something like that. So I'm looking at case A, right, or case B. And somebody says, I think I know the reason that there's a difference between the two. What's the reason for the difference between I have the t sub m profile. I'm just looking at t sub s. T sub s is either look like B or t sub s looks like A. What would make T sub s shift higher? Q double prime is the same. Changing H, exactly. So now let's focus on changing H. So Q double prime is the same. The mean temperature profile is the same, the fluid. So for these two cases, I have that H, I use A and B. That's okay. A, compare it to H of B. The first case A, compare it to first case B. Is it greater, equal, or less? Answer, clicker answer A, B, or C. All right, we'll stop. And let's take a look. Somebody went for D. I think a neighbor has pushed your button. Watch your neighbors. So the convection coefficient for A is lower, hence the delta T is higher, and that's what's shown. So that's correct. Now let's talk about developing and fully developed temperature profiles in the case where we have a constant surface temperature for the wall of the pipe. We had a constant heat flux. But now let's do it for the wall of the pipe. So here's our pipe. We come down. And what's constant? The temperature of the surface of the pipe. I'm really interested in, as a function of distance from the entrance region 0 to become fully developed thermally, I'm interested in a bunch of temperature profiles. This is not too hard of a question. Does the temperature of the surface of the wall of the pipe, don't laugh, is it constant, or does it go up, or does it go down as I go down the length of the pipe? So we'll stop it. And this is the makeup. Maybe you felt abused, the questions are too hard. But 90% of the class is with us on this one. The 10% are torturing me. I don't know what they're doing, but they're torturing me. So that's the temperature of the surface of the wall of the pipe. True? You get that straight. Now, we're going to come in at a lower temperature for the mean temperature of the flowing fluid, which means, is the fluid going to be heated or cooled for this application? Heated. It's going to be heated, true? Now, don't get bogged down with that fully developed zone yet. If you want, push that fully developed zone way over here and tuck it in. It's really close to 0. Okay? So don't think about changing H. This is not the question that I'm asking. But I want you to sketch the temperature of the mean temperature of the fluid that's flowing down the pipe. Will it look something like A or B or C or D? A, B, C, or D? All right, let's go ahead and stop. We always have a rate equation, true? This is the same rate equation that we applied with the constant heat flux boundary condition. What it said was Q double prime is equal to H times Ts minus T of the fluid, the bulk or the mean temperature of the fluid, true? So if I look at it, this really is a delta T. Isn't that the delta T? Isn't that the theta, where theta, this is theta right here, which is Ts minus Tm. So, but when we start to bring in some heat flux into the system, what's going to happen to the fluid as it moves a little down the pipe? Isn't it going to warm up? We're bringing in heat, it's going to warm up. But as we bring in heat, it's proportional to theta, the temperature difference. And the temperature difference starts to go down. So the amount of heat that brought in per inch of length or centimeter of length is reduced. And then the mean temperature doesn't go up as dramatically as it did initially when there was a big theta, a big delta T. So isn't A the best answer? Yeah, A is the best answer. All right, so that's what the temperature profile is doing. Now, let's get back and talk about the H for a second. X. Here is the convection coefficient H, and I do have X fully developed thermally. Now I ask the question, out in this region, is H constant, or is it going to go down, or is it going to go up? So answer A, B, or C. What is my H, my convection coefficient, doing? Is it going up, staying constant, or going down in the fully developed region? Everybody in? All right, we're going to stop it. It's fully developed, isn't it? If it was continuing to develop, then H would be changing. But it's fully developed. So, oh, come on now. That was an easy question, I thought. All right, now let's do this. Now let's take a look at the H in the entrance region. In the H in the entrance region, does it start low and go up? Or is it the same as in the fully developed region? Or is it high and come down answer A, B, or C. And we'll go ahead and grade it. Is the boundary layer thin at the entrance of the pipe? Thin boundary layer? High H. High H. That's our trend. So, isn't that the right answer? Isn't that the right answer? Now, this is theta, true? You could see this theta, how it changes, but I want to plot what theta does, okay? I know that theta, what is theta again? Theta is defined as the local surface temperature of the wall of the pipe minus the mean fluid temperature. Okay, that's what theta is. So, does theta do something like this? I'm going to sketch it. Or does it do something like this? Or does it do something like this? All right, is it curve A, B, or C? What does theta do as it goes down that pipe? Okay, we'll stop it. All right, so what is theta doing as we continue to look at this profile? Smaller and smaller and smaller. And somebody asked the question beginning of class, well, what about this bulk mean temperature? Can it go to a constant value? Could it go to the wall temperature? Would it go eventually to the wall temperature? Would Tm go to Ts? Yeah, for a long pipe. So it wouldn't go to a constant value like half what I'm showing with curve B, that would like half of the initial value. No. It would go towards zero like curve C, wouldn't it? So isn't curve C the best? So we'll go ahead and grade. Oh, look at that. That's great. That's great. That's great. Again, what I did was I shifted over to get the fully developed region out of the way thermally. But if you wanted to, if you really want to explore what happens to it if you are having a higher H, right? Doesn't it come up just a little more rapidly if it's a higher H in the entrance region? I'm not asking a clicker question. I'm just saying I don't want to explore that with a clicker question, but yes, that would be the behavior. It would be a little more rapid than a true exponential. We're going to solve for it in a minute. All right, to it. Let's do an energy balance. This is just a review of what we've already done, but I want to do it very quickly. So think about the constant heat flux condition for pipe flow, and we focus on a little section right here of length dx. And what's happening to it? Well, we're having a change in the mean temperature of the fluid because it's getting some heat transferred into it, isn't it? And so a little bit of heat transfer, del Q, dq, is going to be shown up as a change in the mean temperature of the fluid, dm. So we could write an equation that says for energy balance on that small control volume, that dq is equal to m dot c sub p dm sub t. Do you like that equation? Good. You could also say dq is equal to the constant heat flux at the surface times the perimeter times dx. You like both of those? We did both of those before. We combine these equations to eliminate dq, and we get dt sub m dx is equal to q double prime p divided by m dot c sub p. That's a differential equation. We get an initial condition, we separate, we integrate, we get the equation t sub m as a function of x is equal to tm coming in, tm naught, plus q double prime p divided by m dot c sub p. You say, that's pretty boring. Great. Let's now go to the constant temperature boundary condition for the wall. Let's do the same exact thing, but please don't get lost because we're going to get a startling result. Here's our wall. Here's our little control volume. Think about the wall being hot and you're bringing in some dq. So what is the equation for the amount, let me put it over here, that we brought in, dq? Isn't it equal to m dot c sub p dt sub m? Same equation as before. We also have our rate equation, dq is equal to how much is coming in, but that's not a constant anymore, is it? Times the perimeter times dx. What's coming in is given by h ts minus tm p dx. Do you see that right there? That's the big change. We just don't have a constant heat flux at the wall. We have our rate equation for that. So we have two equations for dq. What do you suspect I do with those two equations? Eliminate dq. When you eliminate dq, you get dtm dx is equal to hp divided by m dot c ts minus tm. Is this tm the same as that tm? It is. Is this a differential equation? First order, we come in with initial condition that tm at x equal to 0, and then we can solve tm naught. Okay. But what's useful is to switch it to theta. Introduce theta equal to ts minus tm. It's just a temperature difference. When we do it, it cleans up the math a little bit. The differential equation becomes d theta dx equal to minus hp divided by m dot c theta. What does theta do? Exponentially decays. And so this is our first order. We have our initial condition, theta at x equal to 0 is equal to theta naught. We then solve the differential equation with the initial condition. We get that theta is equal to theta naught, the initial delta t, e to the minus hp divided by m dot cx. Exponential decay. There's a big assumption in it that h is equal to an average h or a constant. Don't be trying to have it high in the entrance region and doing it. It shifts it. It's not a pure exponential function anymore. All right. So once we have that result, what we can do is we can go to the overall system. I hate to say it. I'm out of time. Thank you very much for your attention. I'll post the lecture from the 11 o'clock. For some odd reason, I was able to go a little faster at the 11 o'clock. I want to do an overall energy balance. And so I have a pipe, and I'm thinking about x going down the length of that pipe. And so x equal to 0, that's the inlet. And let's go ahead and exit at L. So fluid comes in, fluid goes out. Maybe it comes in at the T mean in. What does it go out at? T mean exit. Okay. Maybe it's subject to Ts equal to a constant. We should be able to sketch the temperature profile as a function of x going from 0 to L. We should put in Ts, and it's just a straight line, isn't it? We put in T mean inlet, and we put in over here T mean exit for illustration purposes. And that profile could be something like this. I need to move Tm exit up a little higher. It's an exponential. Maybe my gifts at sketching exponentials needs a little improvement, but there you go. And if I wrote an overall energy balance, would it be that the total amount of heat moved into the fluid is realized by changing the mean temperature? It's going to go out higher than what it went in at. Does that equation make sense? An overall energy balance? True. I can then say I want to use the theta. Okay, so what I need to do here is I need to basically, I'll just do it in two steps. Put parenthesis and put minus TMI there, and then put close parenthesis, parenthesis, and I'm going to put a TS in. So I added a TS, so I need to subtract the TS, and then I put the negative TME here. So I know this is a little algebra, but you just move that one there, and you just added a TS and you subtracted a TS. So you really didn't change the equation, but you were able to express it as Q is equal to m dot C, the theta on the inlet minus the theta on the exit. So the temperature difference between the fluid, this is theta on the exit, and this here is theta on the inlet. We already solved for that theta on the exit is equal to theta on the inlet, e to the minus HP divided by m dot C L. Just use our temperature profile we just had, right? Just use instead of X, put at L. So I take this equation and I manipulate it just a little bit. I'll take the natural log of theta exit over theta inlet. What does that give us? HP L divided by m dot C. I have a, okay, if I switch this, it gets rid of that negative sign. Let me put theta inlet over theta exit, and I get rid of the negative sign. There, I'm happy. And then I use this equation right here, and I say, you know what, from that equation, m dot C, maybe I should color it in blue, m dot C is equal to Q over theta initial minus theta exit. I just took that equation and put it in terms of 1 and then multiplied. So I can cancel the m dot C's. So we find Q is equal to HPL times theta initial minus theta exit divided by the natural log of theta initial over theta exit. And you just stare at this and you say, oh, I love the form of the equation where it's the rate is equal to some convection coefficient times some area times some appropriate temperature difference to drive the flow. That appropriate temperature difference is like an average of this temperature difference throughout the domain. See what that temperature difference is doing? It's dramatically changing throughout the length of the pipe. But mathematically, it's the log mean temperature difference. We now have the definition of the log mean temperature difference. It's the temperature difference on the inlet minus the temperature difference on the exit divided by the natural log of the temperature difference on the inlet over exit. That is the log mean temperature difference. And it's startling the first time you see it. But it's the appropriate right delta T. It's like an appropriate average delta T so that we can get back to a very simple rate equation. Simple rate equation. Q, the overall amount of heat is added, is a convection coefficient, the average over the system. A lot of times they'll put an H bar. What's the bar mean? Average H over the length of the pipe, if it's changing, times the area, times the log mean temperature difference. Thank you so much for your attention. Please read the book. Please study. This is one of those important chapters. Thank you.